afternoon or morning or evening, everyone, wherever you are. Welcome to the SaferSim webinar. Our presenter today is Dr. Chris Schwarz from the University of Iowa. He'll be telling us about an education project that focused on automation with a robotic vehicle. Dr. Schwarz, please take it away.
All right. Thank you, Dawn. Thanks, everyone, for joining me this afternoon. I'm really excited to share this project with you. It's been a few years in the making, and I'll share with you some of the fun we had developing it. So you can see what we've done. So this is, as Dawn mentioned, a project that was designed for education and outreach rather than to answer any specific research aims necessarily. And let me start with some acknowledgements. This, of course, was funded by SaferSim. It's been a journey, and I've had a lot of help along the way. And some of that help was from high school interns that we had through a program called Workplace Learning Connections, which is a great program. And we've had interns from them for probably 15 years or something like that. And I had 9 of them help me with this robot over the course of 3 summers. And then once I got the funding, I was able to pay undergraduate students to come in and help me as well. And there were 4 of them. I see Adi on the call. Hi, Adi. I want to acknowledge a couple of third-party software projects that we made use of. One was for developing a very similar platform to this called Deep PyCar that used a deep learning model. And we made use of that model too in part of this. And then there was another piece of code that we found very useful for streaming video. And I'll show you what that looks like. So the goals of the project were to develop a model, a 1/10 scale model of a car and a trailer, and then integrate sensors and controllers onto it. The main brains of it was a Raspberry Pi. The sensor is a fisheye camera, so everything was camera-based. The main controller for the thing is a DC motor to drive it and another servo motor to steer it. And then the last piece of electronics that we needed was a motor driver controller board that, given the signal from the Pi, you can then use that board to ramp up and down to speed continuously or change direction of the motor. So with all of that, we had a fully functioning vehicle. And then our task was to program this to drive autonomously in a lane. We began with the easier problem of driving forward, and then we drove in reverse. Not just reverse, but reverse with a trailer, which if you've ever done that yourself, then you know what kind of a challenge it is. And key to all this was that we involved students throughout the entire process. So this was a project largely by students for students. So let's back up a little bit. In the beginning, I don't really know if this is the beginning, but it's back in the early days. Nguyen and Widrow trained a neural network to solve a similar problem, back up a truck to a fixed dock from an arbitrary starting position. So move that truck wherever you like. Think of a dock, to unload at a grocery store or something. And then given all of the information you see in this diagram, which we call the state information, the position of the truck, the angle of the hitch, the angle of the steering wheels, then they trained a neural network to back that truck up and do the necessary steering so that it would hit the dock. Okay, so that was done in the late 80s. In comparison, the problem that we are doing in this project is both easier and harder in a way. Easier in the sense that we're just driving in a lane. And so one would expect that the steering angles would be smaller, and you would only have to make minor corrections to stay in that lane, rather than the very large steering that you would expect to do for backing up to a dock. But harder in the sense that we do not have the state information that was listed on that diagram. Things like the angle of the hitch, the real position of the absolute position of the vehicle. We don't really have any of that because it's not something we measure directly. In the sidebar here, I make a note about speed of the vehicle. Is that a state? It is, but in their treatment all those years ago, they did not consider it, because when it's low speed, you can sort of neglect it and it's okay. But the state update, the state information does definitely include speed, and we did include it as well. And that'll have an effect on how much you steer intuitively as you drive on the highway. How fast you're going affects how much you steer. So these are some pictures of the build that we did. We started with a chassis that I was able to buy off Amazon from a company called Seed Studio. Seed has 3 E's in the middle. So I think it came from China, and it took probably over a couple of months to get here. But it has a steering rack on it, so you can steer the front wheels, and it has a little DC motor on it. Now the DC motor turned out to be woefully underpowered once I put the trailer on and some battery packs and stuff like that. So we replaced that little DC motor with a larger one. But you can see how it kind of came together. And none of these pictures is it complete, but you're going to see the complete one very soon. We had a few technical issues along the way. That always makes the journey more interesting. We had a couple of casualties. One was the Raspberry Pi, the first one that we got, fried, and I had to replace it. Probably during the wiring and the testing, we made too many bad moves there, and probably we overheated something or overcurrent. That can happen with these things. They're not, you have to know what you're doing. And then, as I mentioned, the DC motor I had to take out and basically discard because I needed a bigger one. We made a couple of wrong turns. We bought this multi-camera board that you can see pictured here because it advertises that you can plug in multiple cameras to it. So we thought, this is great. We're going to have a camera facing the front and a camera facing the rear so that we can drive forward and backward just based on a software change. But unfortunately, this board, which was the only way we could do this that we could find, plugs into the pins on the Raspberry Pi, and it uses up all of the pins basically. So we couldn't even use the Raspberry Pi for anything else. And then sabotage most foul, the spec sheet for this motor controller that we had basically had a typo on it and swapped the labels on a couple of pins. And that means it didn't work. And my students couldn't figure it out. I didn't have time to figure it out. So it cost a lot of time in the early days just to figure that mistake out. So, but we overcame all that. And first step in the process was to get it driving forward. And what you're seeing are some videos of that accomplishment. You can see we're using a rope as the lane lines, which is very convenient because we can just lay it out and we can make curves and bends in it. The original goal was to use the end of the rope where it has a little U in it. That's the end of the road, right? So you can treat that as a halt line, maybe at an intersection. And we never really got that far enough to program it to recognize it as a halt line. But we could navigate the lane. So our next task was to try to figure out how to do it backwards. And we finally solved driving in reverse this last summer with my most recent student. And the other thing that we did that was really cool was set up this video streaming. So what you're seeing on the right is the perspective of the camera, okay? That's what the robot sees. And it's an augmented reality display, meaning that we're drawing lines that show what the sensors see, okay? Like if you were using a LiDAR, maybe you've seen video of what LiDAR shows on an automated vehicle. This is a much more simpler version showing, we take the image, we feed it through an image processing unit, and then we detect where the rope is, and then the green line is the angle that the controller decides it needs to steer. And so what you can see on the left is it's backing up along the lane, a little slow, but it's getting the job done. And then you can see a couple of colors on that, and I'll talk about the colors in a slide or two. So going one layer deeper now, as I mentioned, this vehicle, we know very little state information directly. But what you do when you don't directly measure the state information of a system is you estimate it. And so we're estimating it from the camera. The exception would be the steering command. So the steering is something that we command in the software. We tell the servo what to do, and the servo does it. And we were able to map the normalized steering, which goes from -1 to 1, to engineering units using a specification for a servo. And so we do know pretty exactly what the steering is because we command that, okay? But we don't know what the speed is. We have no idea what the angle of the hitch, between the trailer and the vehicle is. And we don't exactly know what coordinates of the vehicle, absolute coordinates of the vehicle are, much less relative to the lane. So what we do is we mount that camera to the back of the car. It's not on the trailer, it's on the car. So that if the trailer points off to the left or to the right, we know that the hitch angle there's some angle, between the two. And we sense the trailer using that red piece of tape. And then we sense the lane lines because they're white. And so that information gives us a pretty good estimate of where the trailer is in the lane, what angle it is pointing in the lane, and what angle the car is pointing relative to the trailer. So we can estimate all that information from that. And then the last thing that we'd like an estimate of is speed. And so that's what the yellow tape is for on the wheel. As the wheel rotates, the yellow tape goes round and round and round, and you just have to count the yellow. So let's talk about that a little more. So the problem that we have, if you want to go and build one of these things yourself, the voltage that you provide to the motor is not doing speed control. all right? It's actually doing something more like torque control or flux control. And so it becomes difficult to accurately maintain a constant speed, especially when the loads are varying. And one surprise as we were testing this robot is that as you steer, just the act of driving on a curve or in a circle, as opposed to driving in a straight line, changes the load from the drag of the tires on the carpet significantly. Maybe it would be better if we were, maybe it would be different if we were on a wood floor or a smooth floor, but on the carpet, it made a big difference. So it became kind of nice to try to compensate for that using this speed sensor. That way, when we can tell that the speed is really slowing down, we can increase the command a little more. Now, admittedly, that's a bit of a hack to use this tape like this. Really, what you would do if you were engineering this from scratch, maybe you would get an encoder that might go on the inside of one of the wheels, okay, or on the outside, whichever, and it has a sensor like a light sensor or something that as that encoder rotates, it's a little bit like a fan going around and around, and you can just count the gaps in the fan. It looks a little bit like that. Only instead of one piece of tape that gives us a notification of one revolution, an encoder can do many, many more segments in a revolution. But it would have required us to figure out the mechanical design of installing that encoder. So we made that work. Navigation-wise, we did a few different methods. The one that we finally used for driving in reverse is called model predictive control. And the concept is actually very simple. We're backing up the trailer, and suppose you don't know what steering angle you need to give it, because it's not easy to tell necessarily. Sometimes you need to steer left in order to go right, or sometimes you need to steer right in order to go right. It just depends on the angle of the hitch. So you can basically make a guess or several guesses and simulate what the motion of that car and trailer would be for a short time period, maybe half a second to a second. And then at the end of the simulation, you measure where its predicted movement would take it, and you give that final position a score, or you could calculate its error, okay? Like error in the lane. And then if you do that for 100 guesses, you just use the one that has the smallest error. But the nice thing about model predictive control is that instead of making 100 dumb guesses, we start with one dumb guess, and then we use an optimization routine to make a smart guess and another smart guess and another smart guess that converges to the best input. So that's the way MPC works. And that's the way we were able to get the driving in reverse finally to work. We did, as I mentioned, also make use of a deep learning model developed by NVIDIA and used in that other project, the Deep PyCar. And so we trained that. So what you need to do is provide it with a set of images from the camera that show the world, the state of the world, and you need to give it a set of steering values. The correct steering values. So you need to know the answer for this training set, right? You need to know what the proper steering should be. And then the thing about deep learning is that you need to kind of give it a lot of samples too. But we were able to do that. And now that we have the model predictive controller for driving in reverse, we could generate a training set for the deep learning model in reverse. It's just that we didn't have a way to get the correct steering values necessarily. So, anyway, we have a couple of different approaches now that we can work with on this. This is open source software. You can check it out on GitHub. It runs in 3 modes. It runs in a manual mode where it's connected to a game controller. It runs in auto forward if you have the camera facing front. And it runs in auto reverse if you have the camera facing back towards the trailer. It can use this external camera streaming module, which is really nice it's nice for sort of debugging what's going on, but it's also really nice for visualizing. And so if I ever show this to a classroom or to a group of, to a tour or to a classroom, then all I have to do is put up that streaming video and people can see exactly what the camera sees and what the robot sees. So it's really cool. The image processing is using OpenCV, which is an open source computer vision toolkit that's very powerful. And so since that time, we've used this for a couple of education activities already. One thing, what's pictured here is a conference that took place earlier this year called Ignite, Engineering Success Conference for engineering students. And we did a demonstration of the robot and we used it in an exercise for the students. We've also shown it to groups of junior high and high school students as part of tours. And currently, the robot is on loan to a group of undergrad CS students who are using it in a class project. And basically what they're doing is they're taking the whole code base, which is in Python, and re-implementing it in Java. That's my understanding of what they're doing. They might be doing something more than that, but basically they're working in Java for this, not Python. So already this is being used by students and it has turned out, it has so far been a great tool. I hope it can continue to be. So in conclusion, there are a lot of groups that I'm aware of now or have come into contact that use 1/10 scale cars. They make good platforms for development, proof of concept, education, demonstration, and of course, entertainment. Several professors and organizations who I've heard of that are developing these platforms for their class or for training or whatever are in fact using a 1/10 scale F1 vehicle. F1 as like the racing car. So that's a different kind of chassis, which you could use that. So we went beyond the typical autonomous driving or automated driving to the harder problem of automatically or autonomously backing up the trailer in the lane, which we succeeded at. And we were able to include students along the entire journey. So I was really happy that we were able to include so many students. So a lot of the educational value in the project was actually in the process of doing the project with students. So now that we have a more or less working product with a foundation of code for image processing, motor control, game controller, navigation, this is a nice setup for students to use to do new work, whether to go in and just relearn to learn about how something was implemented or to do new work on a new machine vision or a new deep learning model or a new control technique. And who knows, maybe we could even do some professional research with it on automation and machine vision and things like that. Don't know if it would be suitable for something like that. So that's where we got to, and I'm happy to take any questions.
Thank you very much, Chris. Any participant can unmute themselves and ask a question. If they'd rather not because of background noise, please type it in the chat and I'll read it aloud. I'll give everybody just a few moments to decide whether they have a question or not. Chris, I am so happy that we finally got to do this project. I know you've been working on it and proposing it, and so I am so glad we got to do it. Elizabeth,
Me too.
yeah.
Thank you.
Elizabeth says she doesn't have a question, but she thinks it's a really cool project. Oh, you saw it.
Yeah.
Okay. Well, I don't see anyone typing any questions. I don't see anyone unmuting themselves. So I'm going to assume that no one has any questions right now. Chris can, of course, be found at his University of Iowa email address. And if you just go to dsri@uiowa.edu, you can find all his contact information there. Chris, thank you so much for, I really enjoyed that presentation and seeing the history of the project and the progression of it. Thank you very much, everyone else. And we'll see you next week when we have another webinar. Dr. Justin Mason will be presenting about mapping comprehension in vehicle systems. And so I hope to see you again next week. Thank you very much.